One's a laser, one's a fluid.
Oh. Okay. Where's the laser? Oh, right in the top. Okay. Sorry. Okay. There's a lot of interest in these two-layer models, these various two-layer models with different parameterizations, different kinds of rheologies. And coming from a composites point of view, that's interesting to us, right? We are really interested in these effective parameters and how do you get those while incorporating the geometry and the properties of the constituents that make up that composite. So I'm going to talk about that today, actually, with respect to Wang and Shen's 2010 model in particular. First, let's just talk about what is the marginal ice zone. And there's a couple definitions. One that we like at Utah is the definition where we look at the concentration being 15% at the outer edge and 80%, and then we can streamline this using Laplace's equation, which you heard something about that on Monday from Court Strong. But another definition, probably more appropriate for this, is the part of the ice cover that's close enough to the open ocean boundary to be affected by its presence, like waves. Right? So that's one big part of the marginal ice zone, and that's why waves and trying to understand how they propagate through the marginal ice zone is very important. So with that, I'm going to talk about this particular two-layer model, and this is work coming from Haley Shen and her group there. In this two-layer model, you consider a mix of ice and water, or ice and slush, depending on where you are. Has some height h, and you might set 0 to be sea level. In this case, it's a Voigt material, so you've got a spring and a dash pot in parallel. And you consider an inviscid ocean below that of some height h. And typically you look at some kind of harmonic wave profile that might be incoming, and you have this complex wave number with a real part, and this would be your attenuation rate. So if we're going to look at this from a homogenization point of view, we need to get it at some of the larger equations. And so if we just go back and take a look at the general momentum equation here, what we might consider is a stress, since this is an incompressible material that we're looking at, made up of a deviatoric part and a pressure term, and here force is just gravity, and here U is displacement. And what can go along with this is a constitutive relation for the deviatoric part of the stress, where you have your elasticity tensor. You'll have a strain field, where we're defining this symmetric gradient just as the gradient of the displacement plus the transpose of that gradient times 1/2. We'll have an incompressibility condition. It's incompressible. And this is the form that C in particular will take for the work that we're doing. And it corresponds well to that two-layer model. So here we've defined nu as our complex shear modulus, which will pick the form for that based on the two-layer model. But in general, these two things can be just complex numbers. And we'll define this for tensor here, lambda s, is defined this way. And it turns out, as we'll discover, this is actually a special tensor. But we'll also assume that this is irrotational. We need this to actually get the bounds. So in terms of that two-layer model, when we look at the deviatoric part of our stress tensor, in a Kelvin-Voigt material, this is what it will look like. So you have 2 times the shear modulus. This is your strain. Here's your viscosity. This is not a nu, it's an upsilon, so I'm sorry, those are going to look similar. But then here we have our strain rate. Under the assumption of some harmonic wave propagating through, the strain rate just is minus I omega times the strain. And so if we take that, we can just replace the strain rate with minus I omega times the strain, and the deviatoric part of the stress tensor takes this form. And so we'll actually define our effective parameter this way, whereas in Wang Shen they're just defining it in terms of the velocity using the strain rate. Here we're just using strain and displacement. Okay, so when we come to that, we have our momentum equation, our constitutive relation, and with this term lambda s, it's actually a projection onto trace-free tensors. So because this is an incompressible material, the trace of epsilon is 0. So that means that lambda s contracted with epsilon is epsilon. So our constitutive relation simplifies quite a bit. And given this, then obviously our stress is trace-free, so lambda s will be projection onto that as well. So what we can do then is get a second constitutive relation where we'll define this tensor L to be 1 over 2 times our effective parameter, lambda s, so that L, when contracted with the stress, which it's a projection, will just give us back this, if you solve this first relationship. Okay, so with those things in mind, when we try to do this homogenization, we do it in a quasi-static regime. So this translates to looking at really long waves, long wavelength, these are just 2 pictures of some of the long waves that you actually see in the marginal ice zone. Here you can kind of see these beautiful rolling waves kind of coming through the pancake ice. There's not really any chaotic or short waves going through. This is a picture taken by a UAV showing what looked like plane waves, effectively harmonic waves traveling through. And in this long wavelength limit, what we can do is find some kind of quasi-static regime. So if we go back to just our momentum equation, and we consider low frequency waves as well, we can say that for a harmonic wave, we're looking at something like minus omega squared rho u. So if this is very, very small, we'll take it to be 0. With the boundary conditions for that 2-layer model, if we say that the wave number is very small, which translates to a very large wavelength, especially in comparison to the thickness of the ice, if these things are all small, the pressure really starts to look like just a hydrostatic pressure. And when we substitute that back in, we end up canceling out our forces. So we end up in this sort of quasi-static, well, we end up in this quasi-static state where we've got the divergence of our stress as 0. And this is really key for getting those bounds. Although I should say we did look at keeping some of these terms, but we ended up with what are called signed measures. I'll talk more about measures, and that gets a little hairy. But it's not unreasonable to think that you could do this with some more of these terms. Okay, so what do we do when we homogenize? So we'll consider all the realizations of some random viscoelastic medium. These will be stationary random fields, our pieces here. For one of those, with our set of equations, divergence of stress is 0, our constitutive relations, our irrotational condition, we'll define the effective tensors to be the ensemble average, which ends up also being an integral over Rd, of the stress. So the average stress is then related to the average strain. And the tensor that does that is our effective elasticity tensor. And same goes for L. So the same thing, we're just averaging. So epsilon 0 is the average strain, sigma 0 is the average stress. What we'll do with these definitions in mind is define for our 2-component material, which I'll show you a picture of what that looks like, our elasticity tensor that relates those two, and I'll talk about that more with the picture, and we'll define L in a similar way. But let me make that clear with kind of an image. So the way that we're thinking of this is as a 2-phase composite. We have ice and slush, or you could have ice and water. You'll have complex parameters for each of these. You do have to know those, but those are easier to measure in a lab than trying to measure based on the geometry. But what we'll do is we'll define our elasticity tensor to be 2 times chi1 nu 1, so that would go along here. Chi is an indicator function. It takes on value 1 if you're in ice, takes on value 0 otherwise. And similarly, chi2 takes on value 1 if you're in slush or water, depending on what you're looking at, and 0 otherwise. So it just tells you where you are. Also defines the geometry, times lambda s. And similarly for L. We take those tensors, we put them into our equations. We define the strain and the stress in terms of those averages that we're looking at and this mean fluctuation around those averages, where those fluctuations are given by here some potential function where you've got your strain, it's a symmetric gradient, just like you would take strain, and your stress as a curl of some potential as well. In those situations, when you push through all of the algebra, you derive these 2 resolvent representations. So here we're relating the actual strain to the average strain with this operator where S is defined, sorry, I keep hitting that. S is defined in terms of the 2 constituent parameters, and gamma is this beautiful operator here, symmetric gradient, divergence, symmetric gradient inverse, divergence, which may look familiar from Monday if you replace that symmetric gradient with a gradient. This is a lot like the electric case that Ken talked about. We have something similar for the stress with our operator here. With these two representations, we can then get integral, with those two resolvents, we can get integral representations. So these, by the spectral theorem, give us a representation for the effective parameter. Both of them give us one. Here, f of s is defined as this Stieltjes integral, where mu is a positive measure of a self-adjoint operator, namely gamma chi, and eta is also a positive measure of this self-adjoint operator, and there's our E of s there. And so, but the key point about this is that these measures, they're defined by the geometry of the composite. So, and then those measures themselves will then define the effective parameter through these equations. So you're taking the geometry of the composite itself, if you know the two constituents, and then you're able to use that to learn information about what the effective parameter ought to be. So you're not really curve fitting so much as you are looking at the actual structure and asking what is the effective parameter. And that's the key difference, kind of the important part of this. And then of course the contrasting components, this goes along with that parameter S. So that's great. It's like, okay, we're done. We have it, but the measures are difficult to calculate. They're very difficult to calculate. So we can do other things though. We can bound that effective parameter if we have knowledge of the moments of those measures. The masses of those measures turn out to be just the volume fraction of each constituent. So P1 might be the fraction of ice, P2 would be the fraction of slush or water, depending on what kind of regime you're in. You can calculate the higher moments, but typically those are very difficult. And you would do so with specific assumptions about the geometry. Here, the assumptions you're taking would be the fractions, but here you might assume something like isotropy or some other consideration that you would want to be reasonable before you went on to higher moments. But to actually get bounds, what one can do, you just consider the admissible measures, positive, etc., whose masses match U0 and eta 0. So you might pick two volume fractions of ice and water, that's your only constraint, and then you look at all the measures that share the masses that correspond to that specific geometric requirement, and then what you'll do is vary over all the values of lambda in that integral, and if you know, well, and then I can say if you do know more moments, you can get better measures, but when you do fix those masses, you can show that f of s lies in this circle, where this is the mass to be measured, which is the volume fraction. E of s lies in this circle in the complex plane, where eta is the fraction of material 2. And you can map those back to the common new star plane, where your effective parameter lies, and show that it lies between these two circles. And so in a nutshell, what we're doing is saying, look at all the measures that have the right volume fractions for a given setup, and then vary over all lambda, and get two intersecting regions. The new star will lie between the intersection of these two circles. So if I were to show you what that looks like, it looks like this. Keep in mind that our effective parameter did keep order omega terms, so omega does matter here, the frequency does matter. These are bounds here, the red ones, for a period of 25 seconds, 12 seconds, and 6 seconds. This green line, I'll talk more about where it came from. It's an attempt to get data on this. There's not a lot of data for these kinds of systems. But the idea here is that periods increasing along these lines. And one thing that's interesting when you talk about the quasi-static assumption, if you look at 6 seconds, it's a pretty short wave, you're really starting to violate things. The bounds aren't always, the data's not always inside the bounds. It does a much better job for 25 seconds. It gets worse the shorter the period you take. This is just a picture of that 25 seconds, and just a little bit closer up to show you where some of that data lies. This would be for periods of like 6 to 25 seconds along that line. 6 down here, 25 up here. So where did that line come from? Well, the data that was available is sparse, but it was analyzed by a lot of people here. And in particular, it was taken by Alison Cahoot on SIPEX2 in 2012. She had these buoys that she then placed on ice floes, which had accelerometers, GPS, etc. And then there's some guy getting in the way of the picture. I don't know. And then this is just a picture of the buoy here. But those were just left out measuring motion and being tracked with GPS. So to try to make use of some of that, and I'll explain why I'm talking about this in a moment when I show you the data that I use, but taking our effective tensor, which would take this form if we knew nu star, the effective elasticity tensor takes this form. If we reintroduce that second derivative and realize that these are constants and that lambda s is a projector, this turns into just the divergence of our strain, but it's incompressible, so this just gives us the Laplacian of our displacement. And so we get a wave equation. We get a wave equation with a complex wave speed, if you like, or some complex parameter here. If you consider then just a plane wave and you plug that solution in and find which values for k, q, and omega and nu that they'd have to take for that to be a solution, you get a very simplified dispersion relation, if you want to really call it that. But it is relating the effective parameter to the wave number and to the attenuation rate at a given frequency. So what you can do is then look at the data that was taken. This is derived from that 2012 data, an analysis by Malin and Allison, or by Mike and Allison, from 2014. And what they found is that the energy attenuation rate went about like t to the minus 2, so period to the minus 2, with some other terms, but this of course is the dominant term, where these are the two A's and B's that you see there. And you can get the approximate the amplitude attenuation rate. It's about half the energy attenuation rate. That's for attenuation. For a wave number, there was some data taken in 2001 in a similar way with buoys, where they compared the open water dispersion relation to a measured dispersion relation. And they found that it's close. I mean, it's pretty much open water, but you could treat it with this equation. You've got omega to the 2.41. C takes on this value, and that's this dashed, I believe, dashed line there. But taking these two things into account with this, you can then derive an expression for the effective parameter in terms of frequency. And so that right there is what is making this green line. So this is plotted parameterized by frequency, or you can change it to period or whatever you like. So that's an attempt at getting that kind of data. All right, so for fun, with that wave equation, you can ask, well, can you do anything with that? And you can play some games. Something that's certainly of interest when we talk about wave propagation in the marginal ice zone is absolutely the flow size distribution. This is the geometry that should be defining the effective parameters, but the waves also interact with this, and they have a role to play in creating that distribution. So it's interesting to look at what might happen. And I saw this model earlier presented on Monday as well, but this is from a paper from Dumont et al. In 2011, where they just developed some criteria for failure by wave action. You have a strain failure or a stress failure if the amplitude is high enough. Those produce critical strain amplitudes and critical stress amplitudes. These two values are more or less measured. This one, though, takes into account some ice fatigue, and that goes back to a paper that you worked on, Pat, I believe. And so, but just taking this for what it is, you know, looking at this model, what does it do? Well, with these criteria, you assume the ice flexes with your wave profile. If your wave has sufficient amplitude, it'll break the ice, and then it'll shatter it into pieces of lambda over 2. With that in mind, then you can say, okay, well, what are my attenuation rates, and what are my amplitudes as we propagate through? Well, assume some kind of plane wave, and then what you can do is define your wave numbers, which goes a lot with the wavelength, and your attenuation rates with your effective parameter, if you like, and then you can look at those attenuations in relation to these breaking criteria, and then just say, okay, the distance over which this wave can break ice will be less than or equal to the maximum of those two criteria. So here I'm just taking a logarithm looking for x. So I'm just solving this for x. And you can call this the maximum, or the breaking distance itself, or the distance over which a wave could break ice. You can then, boy, the laser's close to these other buttons. But you can then define an actual breaking distance as the maximum of those two distances. So then you can say, okay, well, the maximum flow size that I should see at a given distance x from the ice edge should be half of the minimum of the set of all wavelengths, such that that wave is breaking at that place in the MIZ. if that makes sense. So the argument basically is that you have whatever waves can actually break, the maximum flow size you will see will be derived from the smallest wave that's breaking ice. Bigger waves may break ice at that distance, but then the littler guy who can still break ice is going to come through and break it up further. Okay. So you have to get the amplitudes right, and this is really also following that 2011 paper, but you can look at various spectra. Here I just looked at the Pearson-Markowitz spectrum. You get a mean amplitude from there. And then these are plots of that breaking distance. This is just an example of the spectrum for amplitude at various peak periods. But using those, you can get some reasonable guess at what your incoming amplitudes ought to be. These are plots for peak period of 4, 6, 7, 8, and 10. You can see they're all different. The maximum flow size that you would see would be below, for a given curve. You can think of it this way. If this is the max flow size, if this is at 150, this point corresponds to a wavelength of 300 meters or something, just twice that. So this is parameterized with wavelength, but your maximum flow size would just be anything below here. So yes, these larger waves, so say at, say at 200,000 meters, yes, these large waves are breaking ice, but it's really here that you would find your maximum flow size, because these are the smallest ones capable of breaking ice. So these would define the maximum flow size you ought to see. And so you can do that for different peak periods, and there's different behavior. And obviously when the peak period's higher, you get further propagation because it's those long waves that propagate far into the ice pack. They have lower attenuation rates. So just looking at this, you can see the peak period depends on those wind conditions. You might get storms that will set up waves that break through the ice. We saw this in Antarctica. In a place where we shouldn't have seen any waves, we started to feel the ice move up and down. We actually had a breaking event as a result, and the emergency response crew, which Ken was a member of, had to swing into action and get people across a crack that had formed in the ice due to this wave action. And it turns out that that corresponded to a big storm, which Allison's had data, or her buoys actually measured. But storms can do crazy things. But when you think about that, then you say, okay, a big storm event breaks up very far. Well, the ice will refreeze if it's left alone with say, some calm weather for a while. So I just thought, okay, well, maybe I had to look at the average behavior instead. So I picked a mean of a 7-second peak period, standard deviation of just 1, and sort of averaged the breaking distance. So I just have what I call the average breaking distance, which is supposed to take into account storm events and then refreezing in some statistical way, I suppose, but just a Gaussian weight on it, on this breaking distance. And it was interesting to do that because for the peak period of 7, and I should say an ice thickness of this goes with having the ice be 0.85 meters here, 0.5 meters here, and 0.2 meters here. That definitely matters. You actually can capture some properties of the marginal ice zone. These black squares are estimated max flow sizes from data, optical images taken in the marginal ice zone. And what you can see is that close, where the ice should be thin, closer to the ice edge, you kind of go through there with your maximum flow size. You pass through the data point. It's a big data point, but there's some variation in it. Then when you get a little further in, the ice might be thicker, and yes, you pass through that too. And in the thicker parts of the ice, where H might be 0.05, you can hit that point as well. So you can actually seemingly capture some of these. If you just hold the thickness constant, an average peak period of 7 does a pretty good job, but you do miss a few things. But then there's interesting things you can do. What if the peak period shifts for a long period of time, and you can ask questions? Is that going to have a large effect on the maximum flow size that you would see? This is just the data that I took that from. So this we saw this picture earlier today. But the way I was getting the max flow size, I'm just saying, okay, for 60 to 80 kilometers in, that was the width of the square. You have sort of an estimation of what your maximum flow size might be. That is, you're not seeing any larger flows, which larger flows are this way. You're not seeing any larger flows after about, I don't know, what is that, 30 kilometer size, so 60 meter wave breaking. So I just wanted to show where that came from. And that was just a fun thing. But surprised that it was a little analytic model that seemed to capture interesting parts or some properties of the marginal ice zone. So just to summarize, for long wavelengths and low frequency waves, we've derived just the first bounds on this effective viscoelasticity of this ice slush composite. And they're rigorous bounds. They're based on the geometry. These bounds depend on the moments of that positive measure, and that positive measure depends on the geometry. So you're really considering that. Those bounds are large, but they are only the first moments. The more moments you know, the tighter the bounds become. So if we calculate more moments, they'll get better. That long wavelength limit, you can look at the simplified wave equation, and you can get some characteristics of the marginal ice zone. Only that example probably only really highlights maybe the idea that you could use some of these to get simple parameterizations of some of these viscoelastic properties based on geometry in some way, but still have low-order models that use them. But we definitely want to do more future work, calculate more moments to get tighter bounds. And there's other things we can do rather than just calculating those moments. Specific geometrical considerations, like I said, they define the moments. One is a matrix particle assumption, where we might say we have the slush and we embed the ice particles in it with specific separation parameters. Those can lead to very tight bounds as well. And we're definitely looking into this actually right now. And so with that, I just want to say thank you. These are the collaborators on this work. Of course, Ken, Ben Murphy, and Elena Cherkaev are both back at Utah, and support from my old school, NSF, MRCN, and ONR. And that's it.
And thanks for giving your time as well. Are there any questions for Christian?
Just to confirm long, what does long mean? I think you said relative to thickness once, but you don't have to be very long to be long relative to thickness. Is that
right?
Reasonable?
Yeah, I think so. For me, it was more about I want to ignore these things. So what does k times h have to be so that it's small enough? So I make this requirement, that it's much less than 1. So in terms of these wavelengths, it is much longer, right, than the thickness of the ice. So I think it would be okay, maybe for meter thick, but then again, I think that would probably be all right. But you have trade-offs, the worse that ratio gets. It's certainly very good, I think, for the pancake ice region in particular. Yeah.
Sorry, there's a question here. You want to ask it? No, you can ask it.
Yep. So really long compared to thickness and the flow size is not important. So the wave.
The flow size. So the way that I think of the flow size itself, if you have a large flow, right? Because so certainly with that wave thing, I'm assuming continuous ice, which may be bad. But if you think of like a large flow, it will interact differently with the wave. I'm not sure exactly how much that matters, but one way that I might actually think of that is that's just a larger volume fraction of material 1, right? Over some length. Right, so it's the size of those flows are defining the actual fractions. And that's all that goes into those bounds. That's the only assumption, right? So if flow size is an issue, right, relative to the wavelength, then that would go into something like the first moment, right? We might consider where the flow sizes are not too big with respect to wavelength, and that would guide your calculation of that first moment, and then provide bounds for that situation. Right? And so those bounds don't assume anything about the flow size in particular. But certainly some of those approximations to get to the quasi-static regime may be appropriate to keep the flow size relatively small, I would think.
Thank you. Is there any questions you look?
I guess that touched on the question in my mind. Just the range of your calculation in terms of peak, how far can you push it?
In terms of peak period?
Yes.
So, you mean take me choosing these bounds?
Yes.
So that's a good question. I did play with going with other bounds. It changed things a little bit. This seemed to fit best. But to be honest, the main reason I chose these is because this was the range considered in the paper where I got these criteria, right? So they were saying that these are typical ranges to consider in the marginal ice zone. So with that alone, I chose those values. Otherwise, yeah, how far you could really push it, I'm not sure. I don't think, I mean, so, and I'm not an expert in exactly all the wave forcing and everything, but there may be some limit to what peak periods you would see.
We'll just have one last question from Luke.
So you're homogenizing these two viscous media. Is there some concept of joining condition between them in the underlying model?
A joining condition that links.
Continuity conditions.
Not really, because you're, and that's because what we're doing is we're really saying that. Well, so flow size really probably is in a sense very important in that way, but we're saying that for these long wavelength waves, right? The microstructure scale, where those kinds of things would be important, is much smaller than that wavelength. So they're not necessarily considered joined. So there's no like this, and that just goes along with just saying, okay, we're looking at a viscoelastic layer, right? But there's no condition that's saying, this one wobbles, this flow wobbles, and transmits some energy to this one via the slush. That's definitely not considered in there. We're just saying we have all these components in a composite, and through those measures, through those integral representations, we can represent these effective parameters. But that's on that assumption that those kinds of interactions are at a much smaller scale than the wavelength that we're looking at, than the larger scale that we're looking at.
Sorry.
No, we have not. We haven't done really any numerical modeling with that. Just sort of looked at it. Oh, composites. Let's apply the theory. Right, cross pollination.
Let's start. Any more questions? Let's continue on the break. But let's thank the Christian and Sergio.